Okay. So first of all, let me welcome you all to the first colloquium, virtual astrophysics colloquium of the University of Athens. We will start today and we will have colloquia taking place twice per month. So the first speaker of our colloquium series for this semester is Tyrone Woods. And a few words about our speaker. Tyrone Woods started his studies in the vast emptiness of Canada in Edmonton, Alberta. I don't know if you have been there, but it is like a huge country. And
mostly empty.
Where he obtained his bachelor and master's degree. And he completed his PhD studies on emission line diagnostics of the progenitors of type 1a supernovae at the Max Planck Institute in Garching, Germany, under the supervision of Marat Kilvanov and Rashid Sunayev. So he then traveled all around the world. So first he met the spiders of Melbourne, where he worked as a research fellow in Monash University. And then he learned about the Peaky Blinders history as a prize research fellow at the University of Birmingham in the UK. And finally, after all of these travels, he returned to Victoria in Canada, where he works as a Plaskett Fellow in the Herzberg Astronomy and Astrophysics Center. So now he's mainly interested in the study of the physics of some of the most energetic events in the universe and the lives of the stars that precipitated them. Moreover, his research involves the study of the interaction of binary stars with the interstellar gas and dust that surrounds them, and he tries to infer the qualities about the stars and their evolution by studying these interactions. Also, his interests extend to other fields, like to the study of the formation of gravitational wave sources, quasars, and the ISM. So today, Tyrone will be talking about the first stars and the birth of the most massive high-redshift quasars. And we are really glad to have you and host you even virtually here in Athens. Thank you for accepting our invitation.
Thanks, Maria. Hopefully I can come visit again in person sometime, eventually. So today I wanted to talk a little bit about some of the first stars that were ever born and the role that they almost certainly, it seems, played in the formation of not just the first black holes, but in fact some of the most massive, earliest high-redshift quasars in the universe. But just really quickly, as Maria touched on, when I'm not thinking about the early universe, I'm usually thinking about supernovae and what makes them and how we can learn more about what makes them. In particular, leading the development of something I've been calling supernova archaeology, which is sort of trying to tease out the properties of the progenitors of supernovae, particularly type 1a supernovae, by looking at the impact different models might have had on the interstellar medium surrounding these events, as probed by the supernova itself as the shockwave plows through the interstellar medium. This has worked out pretty well, actually, and we've, in a series of papers, managed to more or less rule out the sort of textbook single degenerate model, one white dwarf slowly growing by accretion from a red giant companion, that had previously been thought to be the main way you make type 1a supernovae. Of course, there are lots and lots of other interesting white dwarf binary systems that I've been continuing to explore, as probes of the interstellar medium, as eventual gravitational wave sources. This is something that we continue to work on with collaborators all over the world, including right at the University of Athens or the Yorgos. And we're always looking for new collaborators. So if you have an interesting idea along these lines, please do get in touch. Or you just want to know more. But the main thing I want to talk about today is quasars, black holes, and the incredibly important role that the first stars play in forming these titans of the early universe, these behemoths at the centers of most galaxies. In particular, I want to talk about a very vexing problem that has been posed by the observation of objects like this. We now know of about half a dozen or so really, really massive quasars out at redshift 7 and above that reached 1 billion times the mass of the sun before the universe, at redshift 7 was even close to 1 billion years old. And if you sort of stretch that to quasars that are of about that mass above redshift 6, you're talking about a couple hundred. Lots and lots of objects that seem to have gotten really, really massive really, really quickly. And that's baffling. The reason that it's baffling, I mean, it's staggering just to think about things that massive, but if you try to work out how quickly these things must have grown, you can say, let's suppose, for the sake of argument, that these black holes emerged right at the beginning of the universe. They wouldn't have had time to yet, but let's say right at the beginning of the universe. They could be accreting at their maximum rate, the Eddington rate, where if you try to accrete more rapidly, the luminosity will just drive away any additional mass you're trying to accrete. You could maybe, just maybe, accreting at the maximum rate from the beginning of the universe till the moment we're observing them at redshift 6, maybe make some of those 10 to the 9 solar mass black holes. Not at redshift 7, though, even earlier in the universe. And we've started to see some that are actually a few times 10 to the 9 solar masses, even 10 billion solar masses in one case. It really doesn't seem like you could grow these from a sort of stellar mass black hole, something that's 10 solar masses or so, or 30, for instance, all the way up to 1 billion solar masses in such a short amount of time. So how can we get around this? How can we actually build something that massive? Well, one option, if you look at the growth time scale, and you guys can see my mouse cursor, right? Let me know if you can.
Yes,
if we look, awesome. One way that we can, fudge the growth time scale, as it were, try and find a way for this to make sense, is if we play around with this 0.1 here, which is actually, depends on the efficiency of accretion. If we assume some kind of strongly super Eddington accretion, then we might be able to get to any arbitrary mass in a very quick time. The trouble is that there are a few issues with this. The key thing, though, is that most of these first generation of stellar mass black holes, these things that could plausibly have descended from sort of normal pop 3 stars, the first stars in the universe, black holes in the neighborhood of tens to maybe hundreds of solar masses, maybe 100 rather, is that most of them are going to be born starving, as we say. What I mean by that is both the stars that form these black holes, very massive, very blue, very luminous, and the black holes, the accreting black holes that they form in many instances, if they're accreting matter, will be very, very luminous, very, very strong sources of ionizing radiation, very, very good at clearing out any of the gas in their home environment, in the halos, the initial environments in which they are born, clearing out any gas that they might have been able to otherwise accrete and help them grow. They can also grow by mergers within the clusters in which they're born, but these clusters are very, very, very much prone to ejecting black holes and stars in 3-body interactions. It's a very lossy way to try to build a supermassive black hole, and generally there are some ways you might be able to get around it that we'll get to towards the end of the talk, but generally it's very, very hard to envision building something that can get sufficiently massive sufficiently quickly this way. So the other idea, if we look at the time scale equation for trying to grow a supermassive black hole really rapidly in the early universe, is to try and start with a seed mass, an initial black hole mass that is already very massive. And actually, even before, we started to observe these really, really massive quasars in the very early universe, over the last 20 years. But even well before that, there are already sort of ideas, maybe the way you make a really massive, supermassive black hole is by starting with something already very massive. And there are a number of ways that it was thought we could do this. But sort of summarized here, I always like to have somewhere near the beginning The famous Rees diagram, sort of from Lord Sir Martin Rees, trying to map out all the different ways that you might be able to make a supermassive black hole. And you'll see that to the left here, we don't talk so much about sort of the bottom right of this diagram anymore, but to the left here, you'll see that almost all of the roads lead through this weird thing called a supermassive star. Now, this is something that, has sort of come in and out of the favor in terms of the preferred nomenclature. More often now, you'll hear about this channel talked about as the direct collapse black hole channel. And we'll kind of get to why that is and why there might be some problems with that in a moment. But generally, the sort of, if we take it all the way back, the 1960s idea of what we meant by a supermassive star was something in the range of 10 to the 4 to 10 to the 6 solar masses, a preposterously massive star, you would think. Historically, again, going all the way back to the 60s, these actually first came of interest, theoretically, as candidates for the quasars themselves, the first ones to be discovered before we became absolutely convinced these are, in fact, supermassive black holes. Still, they developed an awful lot of theory that we can kind of use here to understand what would a massive gas cloud that is going to collapse to a black hole look like? How would that behave? Well, if you're to take you back a little bit to sort of the stellar evolution classes that you may or may not remember, a very an increasing, if you look at increasingly massive stars, you'll see that as you move up in mass, more and more the gas pressure within these clouds, within these stars or protostars, matters less and less as a fraction of the total pressure. Increasingly, you would expect radiation pressure to be the dominant force holding up these stars if they're undergoing nuclear burning. The gas pressure is going to be just a tiny, tiny perturbation for very, very, very massive stars, even preposterously massive stars like these supermassive ones that were under consideration. A tiny perturbation over what will just be what you would expect if it was entirely radiation dominated for the sort of the local adiabatic index, which is a gauge of the pressure gradient, basically the logarithmic pressure gradient. Now, if you remember your stellar evolution and you look at an adiabatic index that is almost exactly 4/3, say for some little perturbation that depends on the gas pressure, then you know that you're in trouble, because any object that is that close to an adiabatic index of 4/3 is trembling on the verge of instability. As many old textbooks will tell you, any small perturbation is going to be able to trigger collapse. And actually, when you think of a star or just a massive gas cloud, you think of what kind of perturbations beyond just sort of your spherical symmetry, only considering gravity and nuclear burning, etc., would actually play a role. You'd think rotation, you would think magnetic fields. One of the most interesting things about this old literature, I think, is that Chandrasekhar was able to show that even in this, what you would think absolutely classically Newtonian object, you wouldn't think you would need GR. It is so marginal against collapse, so precarious, that you actually do need to factor in post-Newtonian corrections to gravity, because they slightly modify the pressure gradient that you need in order to hold up this fundamental limit on what you need in order to hold up a star, keep it stable, in a way which grows with the mass, just as the gas perturbation that's keeping your gradient above 4/3 falls with the mass. There is a point at which these are going to meet, and it turns out that this comes out to a mass of about 10 to the 5, 10 to the 6 solar masses, if you assume just sort of a polytrope, just a pen and paper model with no temperature dependence of the mechanics of your star. And so this is sort of the idea of where the idea of a direct collapse black hole came from, that if you were to ever assemble something in the order of 10 to the 5, 10 to the 6 solar masses, gas cloud, it would not be able to hold itself up against collapse, but would very quickly collapse to form a very, very massive seed black hole. Everybody with me so far? Any questions?
Not far.
Okay, let's check. So that's all well and good for sort of 1960s theory, but how would you actually ever make something like this? It seems crazy, right? Well, that would have been sort of the consensus answer until about, 15 years ago or so, 20, 15, 20 years ago. And since then, there's been increasing evidence that, well, maybe you can actually make something like this plausibly, but it's not going to look the way that we thought it did in the 60s. The prevailing idea now for how you might be able to make these massive seed black holes or these direct collapse black holes goes a little something like this. You have some initial halos, gas clouds with dark matter in the early universe. Some of them will form sort of your normal first generation of stars that you would expect. Nothing goes crazy here. If, however, you have another halo, a little bit slower in development than these other ones, happening just a little bit afterwards, if it is either very closely synchronized with one particular POP3 star population, or there are a lot of nearby POP3 stars, then there is the chance that it will be embedded in a sufficiently high intensity Lyman-Werner background. So all of these POP3 stars are going to be very massive, so they're very luminous, they're very blue. They're going to be emitting lots of ionizing radiation. But out at redshift, where these things could plausibly be forming, out at redshift 15 or so, the universe isn't ionized yet, reionized yet. So all of that ionizing radiation stays very, very close to the stars that are emitting them. But the Lyman-Werner radiation, the sort of 11 to 13 electron volt radiation, stuff that can dissociate molecular hydrogen but not ionize atomic hydrogen, can travel freely. And if you have a strong enough background of this Lyman-Werner radiation, this molecular hydrogen destroying radiation, then in principle, you could have halos in the universe where all of the molecular hydrogen is destroyed. Now, in a primordial halo, a halo at the beginning of the universe where there's essentially no metals, molecular hydrogen, rotational and vibrational modes, and the emission from these modes are basically your only coolant in the gas. And if you destroy all the molecular hydrogen, then as the halo contracts and contracts and heats up, there's nothing to balance that out. There's nothing to lock it into sort of your standard isothermal cooling track. And so it heats up until it reaches of order 8,000 Kelvin, in that neighborhood, up from, of order 100 Kelvin to 8,000 Kelvin. Much, much hotter. At that point, the gas is hot enough that atomic transitions of hydrogen can be excited and then de-excite, producing emission, which cools things off, and you kind of lock in now to much higher temperature. But both the Jeans mass, the characteristic mass of stars you can form from this cloud, and the infall rates, the accretion rates you expect onto those stars that are forming, scale with the temperature of the gas to the 3/2. And that big jump in temperature means you also get a big jump in the characteristic masses from hundreds of solar masses, normal for POP3 stars, up to 10,000, even almost 100,000 solar masses. And your infall rates, the accretion rates you expect onto these objects, jump up from, 1,000th of a solar mass per year tops to more like 0.1 or even 1 solar masses per year if you really push it. So this gives us a way in the early universe, as long as you have a metal-free environment that is very irradiated, you could actually form these really, really massive objects, but you're going to form them under really, really intense accretion rates, not all at once. And the issue there, and the reason we kind of have to, in the end, abandon a lot of this sort of 60s intuition that I talked about at the beginning, is that you're going to be accreting so rapidly that actually you're going to be accreting, your accretion time scale is going to be much, much shorter than the Kelvin-Helmholtz time scale, the time scale needed to reach thermal equilibrium for a massive star. So your rapidly accreting proto-supermassive star is never going to be able to relax, as they say. It's always going to be accreting faster than it can radiate away all of that excess heat it's pulling in, faster than it can cool. And that means we really can't use these sort of pen and paper polytropic models for these stars. We really have to resort to detailed stellar evolution calculations using a numerical code. Any questions yet?
I don't see anything on the chat so far.
No worries. Okay, so just in brief, there have been a few different groups that have approached this using different codes. Here I'm going to be talking mainly about results using the Kepler stellar evolution code. The couple of nice features about the Kepler code, of course, is that it's a implicit Lagrangian hydrodynamics and stellar evolution code. It hums along at the pace of stellar evolution, going, hundreds of thousands, even a mega year at a time. Usually not a mega year, but hundreds of thousands of years in time steps, until it runs into an instability, at which point it can drop down to very short time steps and follow the subsequent evolution, looking, for instance, at the collapse of the star or things like that. It also includes post-Newtonian corrections and can model the advection of entropy as you accrete material at the surface. So to begin, let's just start by looking at sort of a simple grid of initial models. All of them are going to begin with an initial sort of fluffy protostar of 10 solar masses. We tried playing around with this, looking at 1 solar masses or even 100 solar masses, and it turns out when you're accreting as much matter as we're going to be accreting, the initial conditions in this regard aren't super, super important. We're going to assume primordial composition because remember, if we have metals, we can't really get into the cooling regime that eventually allows for these things to arise. And we're going to assume sort of accretion rates that span the range we kind of plausibly, even on the outside, think we might be able to achieve with these atomic cooling halos that we think can actually form these objects. So in the neighborhood of sort of 1/100th of a solar mass per year, all the way up to 10 solar masses per year. And so what we found is, contrary to what you would expect from sort of the naive application of 60s theory, these stars do not immediately collapse. And the key thing here is that they don't really look anything like the sort of naive polytropes that we thought they would when you're just doing sort of pen and paper calculations. And the key really is that they because they never have this opportunity to thermally relax. Instead of a massive fully convective object that you would expect, if you're Chandrasekhar working in 64, you have a convective core undergoing nuclear burning and a deep and growing radiative envelope, high entropy envelope of all of this fluff piled on top of the star that hasn't had a chance to thermally relax yet. And this actually lets you significantly exceed what you might sort of expect to be the maximum mass tenable prior to collapse by a significant margin. So sort of we mapped out here, this is from our 2017 paper, for the first time as a function of the most important initial conditions, mainly the accretion rate that you assume, the final mass that you expect these stars to finally collapse due to that relativistic instability. And they reach of order 150, 200, even almost 300,000, or about 300,000 solar masses. And they're not short-lived. They don't live a dynamical or a thermal timescale and then immediately collapse. Color-coded here, I've shown objects which collapse while still hydrogen burning, they're on the main sequence and have lived for a significant fraction of their expected sort of 2 megayear main sequence lifetime, and objects that survive past hydrogen exhaustion onto the helium burning sequence. So we see that not only can we form these objects, and not only can they form, but they can actually form long-lived, potentially observable sources. There is no truly direct collapse here. And this is increasingly sort of the consensus. I'd say this is the consensus now. Now, there's one sort of perturbation that I didn't address, which is the idea that, what if these objects are actually rotating? So far, everything has been non-rotating. The issue here is that there's sort of a known problem in star formation just from looking at forming stars in the local universe, which is that if you try to accrete rapidly onto a star, you're not just going to accrete mass onto the star, you're going to accrete angular momentum. And this is going to spin up the star. And if you keep spinning and spinning and spinning up the star, eventually you're going to spin it up to break up to the point where matter at the surface has enough momentum to be flung off. This is actually even worse if you're looking at really, really massive stars, because they are exerting an awful lot of radiation pressure. And so there's an additional sort of lifting force that you need to account for. So we looked into this. Would you still be able to make a supermassive star if you account for rotation? And the answer is yes, so long as you can get rid of almost all, of the angular momentum that you would otherwise be accreting, which sounds like a problem, but the fact is we see exactly the same problem in the formation, not exactly, it's a little bit less stringent, but we see the very similar kind of problem in the formation of, POP1 typical stars today, very, very massive ones. And the answer is that there are a lot of ways stars can shed angular momentum. Both there's magnetic braking with winds, there is torques and instabilities in the disks. Some early results that from a paper that my collaborator Lionel Himmerle later put out for sort of the typical magnetic fields that we would expect these primordial stars to have, along with the pulsational mass losses we expect them to have, of order a thousandth of a solar mass per year. We do expect there to be enough magnetic braking in order to actually stabilize these stars and allow them to keep rapidly accreting. So, with all of that theory out of the way, the idea came about that we should really try and find ways to take this to the next step, try and actually observationally test the reality, the physical reality of these supermassive stars. Are they really there in the early universe? And if they are, how would we know? And how would we know if this is a typical way for forming supermassive black holes in the early universe, or maybe just how we form the very most massive ones and the very earliest? So we brought together a number of people and put together a review that I think is still pretty comprehensive, that came out just 2 years ago, on all the different ways we might be able to make these supermassive black holes, and going into a lot more detail on all of the theory that I just went over. A couple of major ideas to have come out of this that have since continued to proliferate in terms of how we might be able to actually find these evidence of these direct collapse black holes or supermassive stars. The name direct collapse has stuck even if they're not truly direct collapse. We might be able to find them indirectly by looking for massive black holes in the early universe that have relatively small host galaxies, strongly breaking the sort of standard relation that we observe in the local universe between galaxy mass and black hole mass. But it's a very, very difficult problem trying to isolate host galaxies from their quasars, even with JWST. JWST should make it possible, but it'll be tricky. We can also, try and catch direct collapse black holes shortly after they have formed. Shortly because when they formed, they'll form at about 10 to the 5 solar masses. They'll be rapidly accreting, but they'll be rapidly accreting primordial composition gas. They will be able to form before any stars have formed. Other stars may have formed in the halo. And so if we could find a quasar shining, a low mass quasar shining in the early universe, growing really rapidly, with no metals, that would sort of be a silver bullet with no metals evident in its spectra. That would kind of be a silver bullet. This almost certainly had to be a direct collapse black hole born from a supermassive star. But the problem there is that you really have a narrow window because it's only going to be another mega year or two after your supermassive star forms before the first, sort of pop, more normal pop 3 stars begin to die and start to enrich the environment with metals. So there's really just maybe a few mega year window between forming the direct collapse black hole and the halo starting to get polluted with heavy elements, where you might actually be able to say this definitely was a direct collapse black hole. So are there other ways we might be able to find them? Well, if we look well into the future, one way that looks pretty promising actually would be to look for them in gravitational wave detections with, say, the proposed Laser Interferometer Space Antenna, or LISA, which should be flying in 2035 now, I believe it's scheduled. And so what I've shown here is a plot from Hartwig et al. 2018, sort of showing just with the dashed lines in 2 different shades of green, the sort of, as a function of redshift, the expected rate of black hole mergers that LISA is going to be detecting just over time. And just from the normal hierarchical buildup of black holes over time from galaxies merging and the black holes at the centers of these galaxies merging. Shown here for different assumptions about the numbers of supermassive stars out there and the fraction of halos that form more than one supermassive star, which we'll get to more a little bit more on in a minute. We see different predictions for how many of these objects we might actually be able to see merging and when. And because they form at much earlier times, at much higher redshifts, if there are enough out there, if they are a common feature of the early universe in particular, if there are enough supermassive stars out there to be accounting for a significant fraction of the quasar population, then LISA should be able to find over a 10-year lifetime of order a few of these very high redshift mergers happening well before they could be arising from the normal hierarchical growth of galaxies. And so this would be a very promising path to try to actually show, look, this really had to be a direct collapse black hole merger. Another way, though, that we might be able to show that, to test whether these objects are really out there without having to wait until 2035, would be to look for not the black holes, because of all the ambiguities I mentioned there, but to try to hunt for the supermassive stars themselves. JWST, which is going to be launching in December 2018, is going to be able to see supermassive stars, if faintly, only, but there are a number of planned very deep surveys, such as, there's the Canucks survey, which I'm working with, looking at lensed environments. There's also the JADES survey, which is going to be publicly releasing very, very deep data. These are going to be able to find supermassive stars, at some of the latest times, some of the lowest redshifts that we do expect them to form, around redshift 10, maybe even maybe to 7, but more likely around redshift 10 to 12. And so if we can find them, if there are enough of them out there, this would be sort of a slam dunk, definite proof they're really there because we can see them. So Can we detect supermassive stars? Yes, we can actually find them directly. Whether we will is still an open question because, again, there is a lot of uncertainty in the actual formation rate of these objects. I'm talking honestly about a few orders of magnitude at this point in terms of how many, roughly spanning the range from accounting, at the top end, being able to account for all supermassive black holes, at least all of the most massive ones. At the bottom end, really only accounting for these very most massive behemoths, these titans of the early universe, these billion to 10 billion solar mass objects that seem to be able to form by redshift 7. So whether we'll find them or not sort of depends where we fall in that range. The actual number of them out there is a function of not just their formation rate, but also their lifetime. Formation rate times lifetime gives you a number that you can actually expect to be out there at any given moment. We do, however, know that these are rather long-lived objects. As I said, living of order, 100,000 to 1,000,000 years. They are not truly direct collapses. And so if there are, if supermassive stars are on if their formation rate is through this rapid accretion channel is on the high end of what we expect, then James Webb should be able to detect them in the first few years of operation. Their formation rate, certainly in overdense regions of the universe, is of order 1. We should be able to see 1 per NIRCam field of view, so about 10 square arc minutes. So, NIRCam being one of the main instruments on James Webb, we will be able to find these objects. Any questions so far?
I don't see any, but probably we're going to ask you at the end.
Yeah, no problem. That sounds good. Just checking. Okay, so I talked an awful lot about the sort of direct collapse channel. This is sort of a more modern version of that Reese diagram that we saw before by Mar Mezcua, who's in Barcelona now. So I talked an awful lot about this direct collapse channel. This way, one way, sort of now I would argue the preferred way to try and make massive seeds, initially massive seeds for supermassive black holes. But there are, other ways you might be able to do this. I talked about trying to pile a lot of matter really quickly onto sort of more normal POP3 stars, and that there are problems with that, basically, that these things tend to be born starving. They're very good at driving away gas and throwing away a lot of the other black holes that they could maybe otherwise have swallowed up. But there are a couple other ways you might be able to do this. Sort of the classical way that, from the 70s to the 2000s, it was sort of thought you could build up a supermassive object, star or what have you, that could collapse to form a black hole, would be sort of the rapid collapse of a dense cluster of stars. Basically, the idea is that if you have a cluster of stars, much like a cluster of black holes that I talked about before, some of them are going to be ejected in 3-body interactions as all of these stars buzz around within their potential well. Each time a star is ejected, it pulls away energy and angular momentum from the system, and the whole system contracts. If you started with a sufficiently dense cluster, you could have a runaway where, as stars are flung out, they contract, the system contracts, leading to more 3-body interactions, which leads to more stars being flung out, and it runs away until they coalesce and merge into a single object. This is something that, as I said, was explored for a very long time. For the longest time, it was thought, well, and to some extent still is, well, it's really hard to do this and get anything more massive than a few thousand solar masses, really, for the same reasons as I talked about before for the sort of POP3 halos. It's a very lossy way of trying to build up a supermassive object. most of your mass in the system is getting thrown away. And so it's really hard to get above a few thousand solar masses this way. It's a boost in terms of your initial seed mass, but not really enough to get to 1 billion solar masses really by redshift 7. Recently, there has been sort of a hybrid model that has suggested maybe some promise for this. If as these stars rapidly coalesce, they should inflate, much like the rapidly accreting supermassive stars that we talked about in the sort of standard direct collapse black hole channel. As they inflate, because they're accreting more rapidly than they can cool, they present a bigger and bigger target area, which can sweep up more and more of the stars in the halo in which it was born, more strongly promoting growth and maybe allowing you to get up to sort of 100,000 solar masses in this way. But what would that actually look like? Well, there's sort of two different ways. If these things continue rapidly accreting throughout their life, then they're going to look an awful lot like the rapidly accreting supermassive stars that we talked about before. If you zoom in on the accretion history, it may be comprised of many, many 1 to 10 solar mass stars accreting on, but rather than a sort of steady flow from a disk. But it's functionally, for a stellar evolution person, smoothed out over long timescales, looks rather similar. On the other hand, if you really rapidly build them all together, if they really rapidly coalesce, and then as you run out of fuel, you allow the star to finally thermally relax and contract, then you get something that looks a lot like sort of a little bit more anyway, like sort of the old 60s idea. And so we looked at, would these things be able to directly collapse and never actually reach the main sequence? And what we found is that in this other limit of completely thermally relaxed supermassive objects, unless you can get over 150,000 or so solar masses, you're going to make something that is going to collapse while still, only after spending a long time on the main sequence, or even reaching beyond the main sequence. They're still going to make a long-lived object that you're still going to be able to have a decent chance of being able to find in the early universe. So just to sort of round this out, we also looked at sort of arbitrary initial conditions, starting with an arbitrary initial mass and arbitrary accretion rates. Could we finally make something that would really and truly undergo a direct collapse, a dark collapse? It would collapse to a black hole without any long-lived stellar phase beforehand. And the answer is only in really, really extraordinary accretion rates that may be feasible in sort of this mergers of proto-galaxies that I can talk about in the questions if you like, but even then only in rare circumstances. So generally speaking, you're always going to get something which is sufficiently long-lived that we actually have a hope of detecting it. So just with the last couple minutes here, I thought I would run through some of the things that we've been up to in the last couple of years. And the general theme has been, okay, we've looked at the basic initial conditions. Let's try and sort of generalize this. Let's try and look at more realistic initial conditions, infall rates that are drawn from not just fixed, let's accrete 1 solar mass per year and be done with it, but let's actually take and see what happens. Let's actually take accretion rates drawn from realistic 3D radiation hydrodynamic calculations and see what kind of stars we can actually build. And what we found is that you get a remarkable diversity of objects, much more varied than we would have expected, and that anyone else has been able to find before. So these are based on calculations taken from the ENSO radiation hydrodynamic code, simulations of atomic cooling halos undergoing collapse, and they all form a massive disk near their centers with massive infall rates onto a central point source. And we take those accretion rates and we map them into our Kepler stellar evolution code, and we say, okay, what kind of stars would these actually build? And so, depending on the accretion histories, we see objects that look very much like our, sort of constant accretion rates, more step-like structures, or even objects which accrete very rapidly, and then the accretion dies off for a long time, and they almost wholly thermally relax before accretion resumes. So we put out a paper on this, sort of summarizing what we found, which was largely that regardless of these different varying initial conditions, remarkably actually, considering all the different stellar structures that we got, the final stellar masses overwhelmingly almost all fell around 1 to 2 times 10 to the 5 solar masses. There were some trans halos which had more major mergers in the past. Their disks had more angular momentum. They tended to have lower accretion rates, and so they had somewhat less massive, more long-lived supermassive stars, but within a narrow range. All of us assumed, however, that these stars evolved entirely in isolation. But the fact is, what we saw in our simulations, and what more and more simulations are starting to show us now, is that while some supermassive stars may form truly in isolation, others have many satellite disks form. Some just one very massive one. We see in actually the majority of cases multiple supermassive stars forming per halo. At least generally one other companion, more often a few. So right now we're actually finishing up another paper where we want to explore what happens with these companions. What are they doing at the time? Do they evolve to become supermassive stars? Do they form them? Do they collapse to black holes? Do they collapse to black holes before they interact with their companion or not? And what we found is, again, a remarkable diversity from objects which merge while both supermassive stars are on the main sequence, objects which merge after, I say merge, objects which come within the resolution of our simulation and whose disks merge, black hole main sequence pairs, and some objects that are on longer orbits by the end of the simulation that look like they're going to form black hole pairs. So all very interesting. In principle, we have everything from supermassive stellar mergers to black hole mergers to possible supermassive X-ray binaries even. This is all stuff that we're going to need to look into in a great deal more detail, but it's very interesting and suggests there's quite a rich diversity of evolutionary channels in this supermassive star regime. So one last thing that we've been looking at, sort of to continue to look at more and more realistic conditions, is to say, okay, in some of these halos, we're going to have, in the early universe, we may have very strong Lyman-Werner radiation. This molecular hydrogen dissociating radiation could completely destroy all of the molecular hydrogen and leave us a truly atomic cooling halo, something that's going to form really supermassive stars. But if we do, there should probably be lots of other halos where the conditions are more mild, where we only have a very moderate flux. What's going to happen in these objects? Well, even with a moderate flux, although we don't see the formation of supermassive stars, we definitely see, sort of comparing halo B here with halo AA. Halo B has no Lyman-Werner flux, no background. Halo A has a modest one, more typical in the early universe. For halo B, we see, sort of a normal, what we would expect, POP3 stellar population, a generation of first stars, tapping out at about nothing more massive than about 100, a little under 200 solar masses, and not very many stars. But with this moderate Lyman-Werner background and a few other conditions, which I can get into, we see, actually, no, really the only difference is the Lyman-Werner background in this case. We see many more stars form and much more massive stars forming. They do, for a while, sustain this sort of very rapid infall, rapid accretion that we normally associate with forming supermassive stars. But critically, it isn't sustained over the whole lifetime of the star like we see with these supermassive stars. It only happens whenever, based on stochastic encounters between stars and dense gas, clumps of gas within these halos. So one cool observable from this is that we do expect these to form a number of massive objects which will be detectable out at the redshifts they're forming within the LISA band. This is another opportunity where LISA is going to be able to detect here less massive, more like 5,000 solar mass, but still a distinct, actually it's better because it's a distinct signature black hole mergers from these halos. But another cool thing is that these, that might be a little bit more relevant again in the next year with the launch of James Webb in December, rather than waiting all the way till 2035, is that, as I said, some of these objects are going to be stochastically encountering dense clumps of gas and rapidly accreting. When they do, they're going to puff up because they're accreting more rapidly than they can cool. And this is going to push that star's emission to the red. Generally these POP3 stars are going to be, very, very compact, very, very blue. But if they're rapidly accreting, their photospheres are going to expand out, and their temperature will then drop, of course, giving you sort of a red component you wouldn't otherwise expect in these stellar populations. The fraction at any one time that is rapidly accreting is going to vary, but it varies between sort of 5 and 20% over most of the lifetime of the halo that we studied here. So we decided to examine more closely, okay, would we be able to find these objects? Would James Webb be able to detect them and pick them out based on this sort of randomly arising but never not negligible red component to their spectra, ideally just from colors alone? And since I'm just about out of time, the answer is yes, we absolutely can. And this was just published in AppJ Letters a couple of days ago. At the redshifts that we expect these halos to be forming, these not quite atomic cooling halos, but in that direction, not quite supermassive stars, but more numerous. They're much more numerous than typical POP3 stellar populations, and much more massive. And these together make them bright enough to be detectable. But also because they have this characteristic reddening, they are going to be separable from sort of what we would expect for the population of galaxies and whatnot out at high redshifts. So I think I'll wrap it up there and just say that we've learned an awful lot about how you might be able to make supermassive black holes in the early universe. Sort of the supermassive star / direct collapse black hole channel in particular is much, much better understood than it was even just a few years ago. Critically, maybe most critically, we now know what we need to look for in the next year and in the next decade in order to actually test this model and sort out whether this is how maybe just the most massive supermassive black holes form in the early universe, or whether this is a ubiquitous thing in the early universe and that these form the seeds of most supermassive stars. Most supermassive black holes. We don't know yet, but in the next couple of years, we will. And I'll stop there. Thanks.
Thank you very much, Tyrone, for this very interesting and exciting topic.
Thanks.
And also for being in time. Yes, that's really important. So yeah. I think that we have quite some time now for questions, thanks to Tyrone. So please either speak up or type your question on the chat. So everything was perfectly clear.
I try.
Okay, maybe I have a question, if I may.
Yeah, go for it.
So thank you, Tyrone, for your very interesting talk.
Mm-hmm.
There are some points that I would like to ask. First of all, would you expect maybe you have said, but maybe I missed, to see some, now let's take from the beginning. What happens with the Eddington luminosity? I mean, this is basically electrons that are concerned. Therefore, you expect to have to run close to Eddington accretion if this, or it is not totally irrelevant to your assumptions.
Yeah, no. So these will be somewhat close to Eddington throughout, but I mean, in the end, you need to be accreting very, very rapidly, regardless, right?
Mm-hmm.
But critically, you won't be because these things are the boost that you get from having them be stars instead of black holes is that you have a much higher accretion radius, right? You're accreting these at the you know, they puff up to about 10 AU in size. You're accreting, and so there's much less energy emitted as you're accreting, and so the Eddington luminosity is not relevant, basically.
Mm-hmm. Okay, and now about this, what are their observational properties? What do you would expect, for example, for your supermassive stars?
So
what do you?
Oh, yeah, go ahead.
Yes, no. This is what.
So basically, these are going to be. There are some differences in the modeling of the spectral properties, but generally, the what we can agree on is that they are going to be very, very red, and that's probably going to be the main thing that we can pick them out on. They're going to be very, very red, largely featureless objects because they're in primordial halos. There's no metal lines.
Mm-hmm.
They are, however, still going to have a Lyman cutoff because they're not so red that their emission doesn't extend somewhat into the UV, and so that is something that we could try to pick them out based on. There are differences on exactly how blue they can be, but sort of in the neighborhood of 20,000 Kelvin is sort of the hottest that we expect them to be. Redder than the pop 3 stars that we expect, which are around 10 to the 5 Kelvin. But critically, I think they're going to look a little bit like if we're observing them today, they're going to be redshifted to our frame. They're going to look a little bit like brown dwarfs just from the colors, except that they're going to be featureless. There aren't going to be all of these molecular bands that you would expect. You should also see emission from the surrounding halo if they're in these atomic cooling halos. We should see collisionally very broadened Balmer lines and things like that.
Okay. And if I may, I ask
Absolutely.
our convener, Maria, do I have another question?
Yes, we have time for questions.
If you have now some metal enrichment, presumably you are critically dependent on your metallicity.
Yes.
Therefore, have you checked what happens if you have a low metallicity but not negligible, 10 to the minus 5?
Yeah. So I haven't worked on this, but other people have played around with, let's start turning up the metallicity and see where this all breaks, basically.
Mm-hmm.
And it's you get different answers depending on when you basically how you treat mixing in the halo. But it's sort of the highest threshold that you can get is around a few 10 to the negative 5 solar, where you could still where metal cooling would still be weak enough that you could still get into this atomic cooling regime. There's another interesting problem that comes up from the stellar evolution side if you start to include metals. And this actually goes back to some papers in the 80s using Kepler. But if you include metals, so if we think to the evolution of a pop 3 star under sort of normal conditions, quote unquote, what happens when you have no metals? Well, the star contracts until it ignites pp burning of hydrogen, but pp burning can't hold up a massive star. So it contracts, but there's no CNO to ignite, to catalyze CNO burning. And so it has to contract until it can ignite helium burning in order to produce the CNO that can then catalyze hydrogen burning, which can hold up the star. This is sort of a universal thing for zero metallicity stars. What that means for our very, very supermassive stars is that by the time they hit the main sequence, the actual main sequence, they are in a very deep potential well. They've contracted a long ways. If you introduce metals into the star, you no longer need to wait for CNO burning to start. They hit the main sequence before they've fallen into such a deep potential well, and actually they are again so massive, so prone to small perturbations that you can get a runaway nuclear burning that can actually lead, in many instances, to an explosion if you reach the right temperature density regime for the RP process. So there's a paper from 84, I think, kind of mapping this out. And so for non-zero solar metallicities, that can also be a problem as well.
Right. Thank you.
Yeah.
There are a couple of questions in the chat.
Okay.
So by Marcos, who is at the airport and cannot speak right now.
Hey, Marcos.
So great talk. Regarding the seeds that do not evolve or accrete to grow into supermassive black holes, do we have some expectations for the mass function of these objects? And
Yeah,
if
that's... Oh, go ahead.
follow up. And if so, do we have observations to constrain the models?
No, that's a great question. So one of the key things that I didn't have time to talk about in terms of trying to constrain this locally in the local universe is that there is no mechanism in the universe that is 100% effective, right? Not all of these direct collapse black hole seeds are going to get to grow up to be supermassive black holes, one may presume. And so there should be sort of leftovers in the local universe that we should be able to go hunting for. And so what the mass function looks like is something that is still really, really vexes people today. And it really depends on do you think that there's only direct collapse black holes? No, of course not. Do you think that there are no direct collapse black holes? Well, probably not. And so you probably have something that's sort of in between with many intermediate mass black holes, with intermediate mass black holes in the range of 1,000 up to 100,000 solar masses. And then maybe you see a peak at 100,000 solar masses or around that. Maybe you don't, depending on the relative importance of direct collapse black holes. So something that people are trying to do today is look at things like the occupation fraction of supermassive black holes in dwarf galaxies. If there are if most have a supermassive black hole or if most don't, that can tell us things about what the mass function actually looks like. But it's still very much an open question. And we might need to wait for Lisa to start mapping all these black hole mergers to tell us really what the black hole mass function looks like.
Okay, I think Lisa answered the question. So are there any other questions from the audience? I have one.
Yeah, sure.
Maybe two. Mm-hmm. So yeah. Anyway, I have plenty, but
sure.
Okay, my first question is rather simple. I think you showed one plot about the gravitational wave signal expected from these massive black hole pairs. Yes, mm-hmm. Here. And I was wondering if this is computed like with post-Newtonian corrections, or is this like a result based on full GR calculations, excuse me?
No, this is post-Newtonian. This is very simple.
Okay, and yeah. The cutoff frequency there that mm-hmm. you see really depends on the mass ratio of these black holes. So if you had like a black hole which is 5,000 solar masses and another one that is like 500 solar masses, how
it would be very different. Yeah.
So would you miss the signal? Do you know from the sensitivity band?
I'm not sure offhand exactly where we would still get some of it, but I can't do it in my head where the frequency cutoff would be.
Okay, but it has like a dependence there.
Yeah, absolutely.
Okay. And then I was wondering about the calculations the simulations that you showed with these three different stellar structures that you were able to find.
Oh, yeah.
Yes, I didn't quite understand why you were seeing these steps in the enclosed mass, which means that somehow accretion happened onto the star like episodically or something like that.
Yeah,
So,
absolutely. So the basically in that halo, these are just three sort of disparate examples. We actually run 8 different simulations, but these are sort of 3 that showed sort of the variation. In the leftmost one, what's happened is the disk is fragmented, and the fragments are accreting slowly over a long time.
okay. Whereas the second one has like a smooth type of
Yes.
accretion happening through, like. Okay.
And then in the third one, we had sort of the disk emptied out, and then you sort of it just sits and waits for a long time before eventually merging with another smaller disk and starting to accrete from that.
Okay. And I have written one more question here, which I cannot understand right now.
Yeah, I have a quick one.
Yes, until I understand what I was writing.
Sure.
Yeah, so thank you very much for the very educational talk. So I was wondering, like, you make some clear predictions that these things can be detected by JWST. And of course, you said that there are some predictions of order of magnitude of how many of these objects we expect, and it's not very clear. But like, is there a situation that if we don't detect any of them, are we just have to tune some parameters, or we should be looking for some other theory?
Yeah, so we did this. Let me see here. So in this one that just came out, we did kind of some case planning at the end for search strategies. So basically, at the very, very top end, so optimistic that even I don't necessarily think that there are that many out there. James Webb blind surveys could be detecting supermassive stars, and if you sort of these highest predicted rates for supermassive star formation really hold true. If not, then basically the next step is we wait for James Webb, and eventually also Euclid and Roman will find overdensities in the early universe. And then we target those for deep follow-up, because in the densest parts of the early universe, I do actually believe that we have probably a significant number of supermassive stars forming, and sort of more plausible models even suggest that within these overdense regions we should be seeing of order 1 per few NIRCam fields of view. Well, even up to 1 per NIRCam field of view, but there are error bars there. If we don't find any in these overdense regions, so we're talking 2026 by now, maybe 2027, then I would say by that point it would look like supermassive stars are not the main channel for forming supermassive black holes, or even a strong channel. Even as they may make these most massive objects in the early universe, but not too much more than that. If that's the case, we can still find, if these supermassive stars form at all, we could still go looking for these objects with something like LUVOIR. Should be able to detect certainly we did this for the very massive stars, the not supermassive objects, but the very massive, more numerous ones, sort of the failed supermassive star halos. LUVOIR should be able to find these objects pretty robustly, and there are other proposed telescopes that could do similar. finally, yeah, the ultimate answer would come from Lisa, because Lisa should be able to find these things merging. And so if we don't, then we can definitely write it off. But I think by in the next few years, in the next between 1 and 5 years, depending on just how numerous they actually end up being, we should have an answer as to whether they're very important or maybe not so important in the formation of supermassive black holes in the early universe.
Thanks. So we should give you more JWST time to.
Yes, obviously.
So,
okay. I think, okay, my question, I remember I was able to to figure out what I was writing, and probably is a very naive one. But
Yeah.
you mentioned about these two ways of building up these supermassive stars going. Yes, one related to the stellar cluster idea, and the other one, the first,
these
thing that you
rapidly
mentioned.
accreting things.
Mhm.
Yeah.
So I was wondering, is there any way that you can discriminate between these two scenarios by looking at the end result? It wasn't too clear to me. It's only the mass of the star after all, or is it something else?
Yeah, in the end, it affects the structure of the star, but that's also not something that is easily observed, except for, you could argue that if it's very rapidly accreting, it'll be red. If it's formed from the rapid collapse of a cluster, it'll be red until it's allowed to thermally relax, if it's allowed to thermally relax. So it could be blue. I would say it's very difficult just from that alone to disambiguate the two. Something that I didn't touch on is that it is possible to form these runaway cluster supermassive objects with non-zero metallicity. There isn't as much of a metallicity constraint there, and this can lead to unusual objects and these are net results. There's a group here at not at HAA, but at the University of Victoria, where they've looked at if you formed supermassive stars in globular clusters, for instance, in some first generation, they may have belched out from some eruptive events that unusual abundances, which could count for some of the strange features that are seen spectroscopically in globular cluster stars today, odd sodium enrichment and things like that. So that would be one observable you could look for to try and suss out whether these things had ever formed in something like a globular cluster. But that's looking at a different environment and looking at a different mass scale and a different enrichment than sort of the main belt massive black hole seeds that we've been talking about here. So it's a few steps removed, but it is one possible observable signature of something like it.
Yeah, sounds too.
Yeah. It's hard. It would be hard to disambiguate the two. You might, with lots and lots of simulations, we might be able to find some difference in the black hole mass spectrum that is predicted between the
something
two.
related to the population of the black holes that you
but I think that would be the only way to really disambiguate them.
Okay, thank you.
Yeah, I think we are running out of questions, and we should leave you to have breakfast too.
Yes.
Yes, sure.
Yeah, it was great having you and listening.
Yeah, great to see you guys again.
Very interesting topic.
Yeah.
I will stop recording.